let us continue. Before moving on to exactly what we need to talk about today, there's one clearing up thing that we didn't have time for last time. At the end of the last class, we found this Lagrangian. We found x dot squared by 2 plus I chi psi dot minus w squared x by 2 minus chi psi, I think, minus half w prime of x. Okay. We found this operation, if you remember, by taking this 2 cross 2 system and writing down a path integral for it. Okay. Now, there is something a little funny in what we did. And that's something that's a little funny is that we chose to order our operators such that all psi's were to the right and all chi's were to the left. Okay? So that's why we had to write sigma 3. Sigma 3, remember we had sigma plus was equal to 0, 1, 0, 0, and sigma minus was equal to 0, 0, 1, 0. And then we wrote sigma plus sigma minus was equal to 1, 0, 0, 0. Okay. And so we found that sigma 3 was equal to 2 sigma plus sigma minus minus 1. And that was why we got this chi psi minus 1. This was sigma plus, this was sigma minus, this was minus half. Okay. Now, we could have instead ordered all our operators such that psi was to the left rather than to the right. Once again, we would have got discretization of the same path integral, except that where we had psi on the right, it would have been replaced by psi on the left. You remember we had psi's on both sides. Okay? Now, if we had done that operation, we would have had been instructed to write the representation of all operators with sigma minuses always on the left. Therefore, psi is on the left. Okay? So let's try to find the representation of sigma 3 with sigma minus on the left. Okay? So let's do that. So so suppose we write sigma minus, well, suppose we write sigma minus sigma plus. Okay? So that you can clearly see is equal to 0, 0, 0, 1. Okay? And now if we write sigma minus sigma plus, so minus of this, minus 2 times this, okay, plus 1. That will give us sigma 3. Okay? So this is equal to sigma 3. So if we'd done this, we would have got the same kind of path integral representation, but now we would have put psi chi, we would have put, where we had chi psi, we would have put minus chi psi, and then we would have put a plus 1. Okay? Now, neither of these regulators, you see, what we're doing is taking the path integral measure for this fermionic thing and giving some meaning to it. One way of giving it meaning gives us this Lagrangian. Okay? Sorry, with the minus 2. Now this, of course, this Lagrangian would have become a 2 chi psi, but with a plus 1. So this 2 chi psi, so had we done it this way, the net result of this is, had we done it this way, we would have found the same Lagrangian here, but the sign of this half would have flipped to minus half, would have become plus half. Okay? So, you see there are 2 different regulators of the same path integral that differ by this constant term. Now, both these regulators violate t goes to minus t symmetry, because one of them treats the right, the initial state as special, because all psi's are to that side. The other one treats the other state as special. Okay? if we use some way of regulating the path integral that is symmetric between early and late times, okay, some sort of heat kernel kind of regularization, what we find is that we get the average of these two actions. And so that minus sign is just removed. Okay? Now using a good regulator that gives good meaning to your path integral is a good thing to do, because then the measure of the path integral transforms nicely under symmetry transformations. Okay? So maybe we'll come back to this at some point, maybe when we're discussing anomalies. But making what we mean by this path integral sort of symmetrical under all the symmetries we want to preserve in the action is a good thing to do. Okay? So without discussing it in great detail, I'm just going to drop that minus half. Assume that we've regulated the path integral in some symmetrical way. Okay? So this will prove convenient, because otherwise we would have to look at because we want to discuss the supersymmetry of this action. And otherwise we would have to look at the transformation of the measure of path integration under the supersymmetry, and it will have an unpleasant transformation because of this violating of symmetry. Okay? We will perhaps come back and discuss this at greater length in the future. Okay? So right now, we've seen that there are two possibilities. You could have got minus half, you could have got plus half. One of them favors the past over the future, the other one favors future over the past. Sort of seems clear that if you want to keep them both on equal footing, you average. You just drop that. Okay, so that's what we're going to do at the moment, without thinking about it very much. Okay, so with this decision, we've got L is equal to x dot squared by 2 plus I chi psi dot. It's this kind of thing that makes mathematicians very uncomfortable about path integrals. What does that measure mean? Okay, we're more pragmatic than them. W squared x by 2 minus chi psi w prime of x. Okay, this is our Lagrangian, and we're going to work with it. Now, the question I'm going to ask now is, can we see at the level of the Lagrangian that we had this wonderful supersymmetry in our problem?
When we are assuming this, we are implicitly assuming that we are on that particular regularization.
Exactly, the regularization which
make the mistake on that.
Exactly. So this is correct. That was correct with our old regularization. There's another thing that is correct with the old prime regularization, and then there is a more nice regularization. Okay, some heat kernel kind of thing, for instance, which will give us the average of the two. Okay, and we will at some point come back to these issues. Not immediately, because it would just take too much time. Okay, but at some point we'll come back and study these issues, the issues of the measure carefully. Okay, but so right now we're just going to drop that one. Okay, so now I want to understand that the path integral defined by this Lagrangian is supersymmetric. I want to understand how to establish that. Now, of course, I could do it by sort of hit and miss. But the point of studying this simple example in detail is that we introduce techniques that will be useful for us in the future. So now I'm going to explain a technique that proves very useful. And that technique is to rewrite this Lagrangian as an integral over superspace. Okay, so what do I mean by that? Well, let me consider, suppose I've got a new space in which I've got two, forget space, I've got two new anti-commuting variables, which I call theta and theta bar. Okay, these are just two new anti-commuting variables that, like all our anti-commuting variables, anti-commute with every other anti-commuting variable. They anti-commute with psi and they anti-commute with chi. Okay, so I've got these two new anti-commuting variables. And on the space, now I define functions. Okay, so I'm going to define functions of a general function will be a function of theta, theta bar, and time. So far what we've been dealing with is functions just of time. Right? X was a function of t, chi was a function of t, psi was a function of t. Now I'm going to look at just as excursionary mathematics. I'm going to look at functions of time, theta and theta bar. All good? On this space of functions of time, theta and theta bar, I'm going to define the following differential operators. Let me define q theta equals d by d theta, okay, plus I del by del t. And q theta bar, or sometimes we'll call it q bar theta. Maybe I'll just call it q bar. Yeah, q theta bar. Del, and here I should have had a theta bar. And del by del theta bar plus I theta del by del t.
So f is what?
F is any function.
And where you will put it in the ladder?
We will see in 2 minutes. Okay, at the moment I'm just doing some mathematics. These are differential operators that act on functions like f. How that is connected to the Lagrange, we'll see in a minute. Okay, now the point of these two things, these operators, is the following. Clearly q theta anticommutator is 0. Why? Because this is a derivative with respect to theta, but here there is a theta bar. Okay? So the derivatives don't talk to that variable at all. And we described last time how the rules for anticommuting numbers tell us that when you take a derivative through another anticommuting number, you pick up a minus sign. Okay, so clearly that's true. Similarly, q theta bar with q theta bar anticommutators. This is also clear? Okay. What about q theta with q theta bar? What about this guy? Well, let's see. This guy has one non-trivial term. It's this derivative acting on this. And the other order has another non-trivial term, which is this derivative acting on this. So can you see, sort of by I, that this is going to be 2I del by del t. The only non-triviality is because derivatives act on variables. The two derivatives anticommute with each other. The two insertions of theta and theta bar anticommute with each other. So the only issue is derivative with theta insertion. And we get, since there are no signs, 2I del by del t. But you know, in quantum mechanics, I del by del t, according to Schrodinger's equation, is the Hamiltonian. So this is implementing the supersymmetry operation q theta bar is equal to 2h. Now, if you remember our complex supercharges from last time, q1 plus iq2 and q1 minus iq2, obeyed this algebra. We could have done this in real terms, but it's just much more convenient to work with these complex guys. Okay, so this is going to be, on superspace, these differential operators will represent supersymmetry. Okay. Now there's lots we have to learn about superspace. It's the first fact we've encountered. Now this next thing we do is to define two new differential operators, and this is really what makes the game interesting. Okay, or useful. And these two new superspace operators are d theta, which we will define, and people use all kinds of conventions, but we'll try to be as simple as possible. Or sometimes I'll call it d bar theta, is del by del theta bar minus I theta del by del t. Okay, all good? So now we've got these two new differential operators, which look pretty similar to the supersymmetry operators. Now, if you compute the algebra of d with d theta bar, d squared will be 0, d theta bar squared, d bar squared will be 0, and d anticommutator d bar will give you minus the Hamiltonian, minus twice the Hamiltonian. Not that that will be of importance. It's sort of almost like they implement almost the same algebra as the supersymmetry. By making one of them minus of the other, we could have made them implement the same algebra as the supersymmetric algebra. What is important is this. The important thing is that Q's and D's anticommute with each other. Okay? So Q with D, irrespective of what we put here, unbar with bar is equal to 0. Why is that true? First, let's look at Q theta with D theta. Well, that obviously anticommutes because both of them have derivatives only of theta or insertions only of theta bar. So for the same reason that Q squared, Q commuted with itself, Q and D anticommute with itself, obviously. Okay? What about Q with D bar? So let's see, what about Q theta with D theta bar? This is less clear because you get two terms, both of which are non-zero, but they cancel each other. Okay? So let's look at the term where you have Q acting on D. That will have the term where this D by D theta hits this minus theta. So we will get minus I d by dt. But we will also have a term where this guy hits that, and that will be plus I d by dt. Because one came with a plus, one came with a minus. And so we get 0. And all the other facts can be proved similar. All clear? So, what we have is this new superspace derivative, this d theta and d theta bar. These two new superspace derivatives anticommute with the supercharges. Okay? Now, what does that mean? You remember that we were interested in these q thetas, these differential operators as implementing symmetry transformations. Right? The idea was that the q theta had the same algebra as supersymmetry, so it will actually implement the supersymmetry transformations in our new superspace formalism. Now, because in general, if you take some function of theta, theta bar, and time, and you do something funny to it, let's say I multiply it by theta. Okay, then the action of q on this will not simply be theta times the action of q on f, because q will also act on the theta. So, if you take this f and you expand it in fields, as we will do, we write it as a plus theta, let's say, zeta 1 plus theta bar, zeta 2 plus theta, theta bar, some b, something like that. Okay? And you take this as the superfield of interest. We'll come back to actually what we mean dynamically, but just as an algebraic point. Take this as superfield of interest, and you say that the transformation of all their components, A, xi1, xi2, b, is given by the action with the super derivative, this q acting on the superfield f. Okay? That will give you some rule, and we will study this rule in detail in this class. But that will give you some rule for how all these components transform under supersymmetry. Okay? Now if you make a new superfield, which is like theta times f, because q also acts on the theta, then if you say that your rule for how things transform is given by the action of q on theta times f, you will get a new rule. Okay? On the other hand, if we weren't doing this random thing of putting some general function like theta, but instead we acted with the d derivative, because q anticommutes with the d derivative, that object, the composite object, if the components of the original f transform under, if f transforms under supersymmetry according to the differential operator q, then df also transforms under supersymmetry according to the differential operator q. Okay? So D is an operation that you can use to act on superfields without changing their transformation, that involves theta, and yet does not change their supersymmetry transformation properties. Okay? So, good. Now I'm going to try to use these ideas to try to build the supersymmetric Lagrangian for the model we were studying. And then we will check that we get back the answer we started with. Okay? So consider a superfield X. And it's going to be expanded in this form. We'll go through exactly how the expansion goes in a minute. But consider the superfield X, it will be expanded in this form, or roughly in this form, where xi1 will be chi and xi2 will be that's psi, our two fermion fields, and f will be, this b will be something else. We'll see how that goes. Okay, but it's just an arbitrary superfield. The most general superfield has an expansion in this form. And consider the Lagrangian that you write, but that you get d theta bar. Okay, d theta bar x. And I think when I worked this out, I got a minus half, but we will have to confirm that. So I'll put minus half here. Minus half plus I of x, where I is the integral of w. So I is the function whose derivative equals w. W, remember, was our superpotential. Okay? Find a function whose derivative equals w.
This is capital X,
I of capital X. Okay? This, I claim, gives us a manifestly supersymmetric Lagrange. Now, why is that true? Okay. What is the rule? So what are the fields in our problem? The variables in our problem? It's capital X. What is the rule for the transformation of the components of capital F? Well, the transformation rule is that it's the transformation rule that follows by acting with q and theta. We'll explicate this in great detail as we go along. Okay? So you act with q and theta, expand what you get in an expansion in theta and theta bar, and equate coefficients. That's the rule for supersymmetry transformations. Okay? But because of the fact that d theta and d theta bar commute with the supersymmetry operator, the transformation of the whole Lagrange, whole thing, apart from the integral sign here, under the supersymmetry operation, is just acting with q on this thing itself. Please. Yes, capital X is a superfield. Capital X will be like one of these F guys.
But then W had an argument which was purely small x, I thought.
W has an argument. Correct. But it's a function of a variable. And we replace that function with capital X. Okay? Right. Thank you. So W is just a function of one variable, and in that variable we put capital X. Okay. So, claim, if I act on this whole thing with q's, okay, the transformation, if I transform x by q, is simply given by q acting on this whole thing, which I'm going to call f. This is because this is true here follows from, let's say, the chain rule of partial differentiation. For instance, if this was x cube, q on x cube is simply qx times x square plus x qx x plus x squared qx. Notice that the whole field x, being a superfield, both these are anti-commuting numbers. The whole field x and commutes through with q operators. Okay, so that's something you can easily verify, this chain rule. So you just act with q on a function, but that's the same as acting with q on all its components. So just transforming x after you open it out. Okay? Right? And similar statement holds for this because the d operator anti-commutes with the supercharge. So this whole thing here is just the thing that you get by performing the supersymmetry operation, the variable change on our dynamical variables. It's just the same thing that you get by acting q on this full object, regarded as a superfield in its own right. Okay? Wonderful. So now let's take that f, whatever it is. Please.
So we need 2d, right, always, because there will be a minus sign.
Say again?
We have 2d, it's quadratic in capital D.
It will always be quadratic in capital D. Yes, it will always be, because we want our Lagrangian to be in the end a boson.
No, I'm saying because, also because there is a minus sign.
Because when you take one through.
Q to D.
Q to D, yes. But it will always be quadratic, if that's the question. Right, yes. The minus signs don't, if you just look at it carefully, it doesn't trouble us. Thank you, but it's a good question. Good, excellent. So now we've got, where were we? So we want to look at what we get with acting on Q and F. F has this general form. So let me act with Q theta and F. So Q theta has two terms, one which is del by del theta acting on F. That gives you, let's say, zeta 1 plus theta bar B. That's the action of del by del theta and F. And it has terms which are theta, and it has terms which is I times theta bar, so plus I times theta bar, and then the time derivative of whatever by itself did not have a theta bar. So the time derivative of these quantities, A plus theta zeta. Because we're multiplying something by theta bar. So if there was a theta bar left over, we would get theta bar squared, which would be 0. So it's only the terms without a theta bar to start with that would appear. Okay. So we take that variation and then we multiply by d theta bar. And we act on this. But now you guys remember what d theta bar meant. It was same as differentiation. So the only term that this picks up is the term with two thetas, one theta and one theta bar. So exactly here we would get I times zeta dot dt. But I times zeta dot dt is a total derivative. So the variation of the action under the change of variables generated by this differential operator, this q theta differential operator, is by a total derivative. Independent, what? Zeta was, I'm sorry, it was, I think what I called zeta 1. No, what I called, yeah, zeta 1. Zeta 1, it's this guy. Independent of any details of what's going on. the variation under Q of a superfield, the term with a theta and a theta bar is a total derivative under time. Now, any change of variables of an action that has the form that if you make this change of variables and then the action changes by a total derivative, any such change of variables is a symmetry operation. Those of you who, there's this beautiful derivation of the Noether charge for such a symmetry operation in Polchinski's book, in which you get pi delta q plus the term involving the total derivative. Right? You can figure out the conserved current. Those of you who have done the string theory course know this very well. Okay? So this is the general framework of symmetries. Changes of variables, small transformations of variables, variable changes, that under which the action stays unchanged. Action has the same form in terms of new variables as in old variables, up to a total derivative. So this formalism guarantees that if we build an action out of our basic dynamical superfields, making them only functions of d thetas or anything that commutes with supersymmetry. Another thing that commutes with supersymmetry is d by dt. So you can make it out of d by dt. So you can make d theta or d by dt with these derivatives acting on your basic superfields will automatically be invariant under supersymmetry transform. Is this clear? Okay, I'm going to make, because this is the beginning of our course, today we will see this in great algebraic detail as we go on. Okay, but is the basic point clear? It's a very simple point.
You think you can add a q theta of f with the action?
Q theta of f.
Because it's adding some total derivative term.
If I just added a q theta, that would be right. I could do that. But if I added q theta times q bar theta, q theta of f times q bar theta of f, I'd be in trouble. Because it would be total derivative times something.
Anything you can add.
What?
Anything, q theta of any function,
not of anything. But if I add q theta times q bar of some function times q bar theta of something else, then I would be in trouble. Yes. Correct. So it would not be a total derivative. So for instance, here we could not have made this q theta q bar theta. It was very important that that was d theta d bar theta. Yes.
then with q bar theta we will have a total derivative. That's why you were saying it's correct.
What? With q bar theta, yeah. So let's try what Shuman's trying. Suppose we add a q theta times f. Okay, let's open it out. Okay, so I add a q theta times f. First I get the theta derivatives. So I get zeta 1 plus theta bar b. And then whatever else remains will be a total time derivative. So I don't have to worry about whatever else remains. Now this never has two terms with theta and theta bar. So will not contribute to the integral d theta bar. Okay, so it's just that adding this term here to the Lagrangian was itself just adding a total derivative. Okay, so it was a trivial operation. So it's not, not just that the symmetry transform of it was trivial, the term itself was trivial. So it was not a very interesting operation, but you could do it. Is this clear? Okay, now just see the algebra again here. Why was it that q theta on f, that the variation, if we had integral f, q theta on f, why did it turn out to be a total time derivative? Well, there are two terms, right, when you act with q theta. There was the theta derivative and the time derivative. The time derivative will give you a time derivative, fine. Why didn't the theta derivative contribute? It's because this integral measure also has a theta derivative. So if you have a theta derivative and another theta derivative of any function, you get 0. So the theta derivative never contributes. This is the fermionic version of a total derivative. Integral of a derivative is 0. So this q operation was almost a total derivative In theta, the part that was not was a total derivative in time.
There is theta bar, but that also cancels.
What?
There is theta bar.
Where is the theta bar? It doesn't matter. That's just the theta derivative. The theta integral itself kills it. Right? Because this here, if this is what you're saying, Chintan, this here was d by d theta bar. Now we take this to this side at the expense of a minus sign, and that itself kills the d by d, because d by d theta squared is 0, irrespective of whether there's a d by d theta bar or not. Right? Excellent. So this is the reason that this works so nicely. Okay? We've seen this in this extremely simple example, but as we move on with the course, we will, with less comment and with less checking, use it for more complicated examples when we look at 4-dimensional supersymmetric theories and so on. But it's always the same mechanism. Is this clear? Yes?
This is why we define the integral to be the differential operator.
Yeah, I suppose. You know, it's always, this is a great thing about the definition. Now, you know, it's always very hard to know the people who originally defined what was their thinking. But
Because the double derivative.
right, it has this property, for instance, that integral of a total derivative is 0. Yes, right. That's a great property to have.
Total derivative is a boundary.
Not in fermionic integrals. There's no boundary of, you know, it's only a formal integral. Right? So you should think of the fermionic integral as being like the analog of a compact bosonic integral, with no boundary. Okay, excellent. Excellent. So now we want to go on and see this actually working. I want to show you that this Lagrangian, precisely this Lagrangian, and if I've got the signs right, and I hope I have, precisely this Lagrangian reproduces the Lagrangian we got at the end of the last class. Okay, the Lagrangian we wrote at the top of that board. Okay, so I'm going to work this out in painful detail for you people. Once. We'll never do this kind of thing again. Okay, but let's try to work it out in painful detail, and let's try to get all the signs right, and you guys will help me, right? So I'm very bad at this. Okay. Okay, so but just to start off, I've written down what I think that the right expansion is, and if it's not the right one, we will correct it as we go on. So the actual expansion I'm going to make in terms of the variables that we talked about before is x is equal to little x plus I theta chi plus I theta bar psi plus I theta theta bar f. This f has nothing to do with this f. I should have called this something else. I'm sorry. Okay, this is just some general superfield. Forget about it. That f is not a superfield. It's a regular field. It's function only of time. I use it because it's standard notation. When for this, as you will see, it will turn out to be what people call an auxiliary field. It's standard notation for this auxiliary field. Okay. So this is my expansion of the superfield, which I hope is correct, in terms of the physical fields we talked about last class. And to check that it is correct, I'm now going to check what we get when we take this, plug it into here, and evaluate it. Okay, that's the game. Okay, so we want d theta. What? This f has nothing to do with that f. This is a function only of time. It's not a superfield. Right? We've just done the most general Taylor expansion of the superfield X, and I've put some I's so that I think it will match with the conventions before. I may have put them wrong, we'll see. Okay? Great. So now I want to plug this in. So let's do it in cases. First we will evaluate d theta x. So d theta has two terms, one which is d by d theta. Okay? So with my conventions we get I chi plus I theta bar f. So far so good? The d by d theta terms are on. Then d theta also had an I theta bar. So let's write that down. Plus I theta bar. And then we had a d by dt. No. D had a minus I theta. Q had a plus I theta. Oh, you're right. D. Thank you. See, already you helped me there. Thank you. Minus I theta bar. Because we've written D. Thank you. Okay. And then, now we only act on those terms that didn't already have a theta bar. Because that gives you 0. So we get x dot minus I theta chi dot plus I theta yes, because there's a minus out here. Thank you. Okay, so let's simplify this. This is I chi plus I theta bar f minus I theta bar x dot and then plus theta bar theta chi dot. Now when we get a theta bar theta, I'll always write it as theta bar, just as a convention. So that's minus theta bar chi dot. All good so far? Okay. Now let's look at d theta bar x. This is equal to, so first the d by d theta bar terms. So that's I psi. Now this will give us minus I theta f. Right? Oh, thank you. I did this wrong. What? D by d theta. What? Say again? Are also a function of time. It is the previous chi and psi. This, if I've got my variables right, they will be the previous chi and psi. Okay. I'm unsure of that. I tried it over 15 minutes, the last 15 minutes before class. It's a fermionic variable. That's a good question. Chi and psi are fermionic variables. They anticommute with theta and theta bar also. Chi, psi, theta bar, the 4 fermionic variables in the game. F will be bosonic, right? What? F is bosonic. F is bosonic, X is bosonic, chi and psi are fermionic. Okay, excellent. So d theta bar x, we got I psi and minus I theta f. Minus because I had to take the d theta bar through the theta. Okay? And then we had minus I into minus I into theta bar, into theta. So now we ignore the terms which already have theta in them, so this and this. So we get A plus theta bar, so ignore the terms that already had theta in them, which are this and this. So we get x dot plus I theta bar psi dot. Okay? And then please correct me if there's any mistake. Which is equal to I psi minus I theta f minus I'm sorry, here I should have grouped. So this is I f minus x dot. And here I get minus I theta plus I theta into minus I theta into x plus m. Okay? F plus x dot. And plus theta bar psi dot. Please correct if there's mistakes, because one minus sign here can kill us. Okay, that's why we'll never do it again. It's the kind of thing you do for papers and okay, yeah. Okay, excellent. All good? Okay. So now what we want to do is to evaluate minus half d theta d theta bar, d theta x, d theta bar x. Okay. Sounds sort of daunting. So what we want to do is to pick up the theta bar terms in the product of these two and to keep track of signs. Okay, so let's do it. Let's first evaluate without this minus half. That's almost guaranteed to give us trouble. Let's first evaluate it like this. Okay, so we have d theta x here. And so you see now there are 4 kinds of terms that will contribute. The simplest, well, all kind of term is theta bar here and nothing here, and vice versa. Let's capture those terms first. So there's this, okay, times this. This genuinely didn't have an I, right? Yeah, okay, good, it didn't. So this times this. Now because it's theta bar, but the integrals are d theta bar, that flips this sign. So it's, I get chi dot psi with an I from that term. Do you agree with that? Okay? Then let's get the other one. That's this with this. Now this is theta bar, so we'll have to flip sign. So we get minus chi psi dot. And there is an I. Okay? But now we integrate by parts. Hello? Hello, yes?
Hi, Siraj, this is Anshuman.
Hi, Anshuman, I'm teaching a class now. Can you call me in a couple of hours? Is that okay? Yeah, see you. Okay. First term. First term should be psi chi dot. Let's say. First term was this with this, right? Okay, and the next term was this with this. So always chi is on the left. Okay, now we can integrate by parts. Okay, and make these. So this becomes 2I chi dot psi. Okay, great. Then there are the terms where we have, so we've got these terms, now we've got the terms which were linear in theta. But here things are a bit simpler than they could have been, because you see, this guy has only theta bar and this guy has only theta. It comes in the order theta bar theta, so there's no sign. And I with minus I kills it, so there's no sign. So we get plus f minus x dot, but there was a minus sign here. So we get minus f minus x dot in what? The I minus I. Thank you. So there was plus. Thank you. Thank you. Okay. Wonderful. And that's it from the d theta bar terms. Okay. So this is equals minus x dot squared plus f squared plus 2I chi dot psi. Now that was when we didn't multiply by the minus half. So when we multiply by the minus half, we get minus half d theta bar d theta x d theta bar x is equal to x dot square by 2 minus f square by 2 minus I chi dot psi. Okay, now if we've done it right, this should match the kinetic term. Oh, the fermion is messing up. Huh? Oh, you're right. Thank you. Thank you. Yes, perfect. Thank you. So we can write this as I plus psi dot. Perfect. Okay, good. So I may even have got the expansion fields correct. Yes. I chi psi dot, that was the one we changed into psi, chi dot psi by integration by parts. That's why this factor of 2 came. So sorry, I should have written it and then written it again. Thank you. Excellent. So this is half our action, at least we've got the kinetic terms correct, so looks pretty good. Okay. Now there is the other half of our action, which was, now we'll evaluate. So let's circle this. I wish there was some color. Oh, there's some yellow. Let's circle this so that when we want to refer to it later on, we can find it. Okay. Now, the next thing we want to do is to evaluate integral d theta bar I of x. Right? Now, how do we evaluate this? I of x could be any function. Well, that's not a problem. We just Taylor expand. You know, we Taylor expand around capital X equals little x. Theta should be thought of as small because the power series expansion in theta terminates. Okay, so I choose the expansion point as little x and I Taylor expand. So this is equal to integral d theta bar I of little x plus I prime of little x. Now, the term that will, there are many things, but I'm only keeping track of those that will contribute with when it hits the theta bar. So the only expansion coefficient here that I need to worry about is the I theta bar f, because the terms that were linear in theta and theta bar will not contribute. Okay, so I prime times I theta bar f. Okay, there's another term, but I'm not writing it because it's not going to contribute to this d theta bar integral. That's clear, right? Okay, and then plus there is a second derivative term, which is I double prime of x by 2, and then only those terms that will contribute when we take to second order, but those are I theta chi plus I theta bar psi square. Not all terms in that square will contribute. Two of the terms are 0 because theta square is 0 and theta bar square is 0. But the theta bar term will contribute. Clear? Taylor expansion, yes. All I'm doing is taking this function and expanding it in a Taylor series around the point little x. So capital X, let's look at this. Capital X is little x plus this object. So I'm choosing little x as the expansion point for the Taylor series. Now, why is that? I could have chosen any expansion point. But why is this a good thing to do? Well, for two reasons. First, I'm interested in making functions only functions of bosonic, the variable x. But more seriously, it's because the power series expansion in this will terminate. Because theta squared Yeah, so it's, I mean, I'm just Taylor series expanding so that my coefficient functions will all be functions only of little x. Is this clear?
Yeah, so you are derivative with respect to which?
Derivative with respect to the argument. The function is a function of an argument. It's a derivative with respect to that argument evaluated at the point little x. Is this clear? So like Shuman asked at the beginning, I was a function of some variable, just a function of a real number. I'm taking the derivative of that function. Is this clear? Could be sine x. Excellent. So now we just simplify this. So now we just simplify this. So this term was I didn't need to write because it's not going to contribute. This term by itself gives me I prime of x minus I prime of x. Minus because d theta bar, and this was theta bar. Okay? And this term here gives what? What's again? Yeah, thank you. There's an F. Thank you. Thank you. Okay. And then this term is what? Well, when we open this out, hello. No problem. Is this clear? Okay? Tell me if I've messed up on signs, please. So I will get, and then the integral just kills that theta bar theta. So I get plus I double prime of x psi chi. Do you agree? Okay. So now what I wanted to do was to evaluate minus half plus this. Minus this thing plus this thing. I hope I've got it right. So that evaluates to x dot square by 2 minus f squared by 2 plus I chi psi dot minus I prime of x f plus I double prime of x psi chi. Now remember what I was. I was the function whose derivative was w. Therefore, I prime is w. So we'll make that replacement. And I double prime is derivative of w. W prime if you want. Derivative, whatever. Yeah, let's call it w prime. Okay. Now, you guys might be saying, well, This is a valiant algebraic attempt, but it was a stupid attempt because right from the beginning you knew you were doing something stupid because the number of fields you had in your expansion didn't match what we had in our expansion. Okay, you've got little x, okay, you've got chi, okay, you've got psi, but there's the elephant in the room. What about this f? Nobody asked me that question, so I didn't say anything about it. But now we're in a position to answer it. We're in a position to answer it because you see, f is not truly a field in the Lagrangian because there are no derivatives, time derivatives for x, f. Therefore, the path integral over f, okay, is a local thing. It can be done point by point. You can just do the path integral without, it's pointwise you do the integral. And doing that integral, because the path integral over f is Gaussian, apart from overall measure constant factors, number constant factors, which we're not keeping track of, can just be done. We can just do it by solving the equation of motion for f. This you know, right? That the path integral for a Gaussian variable is the same as just solving the equation of motion for that variable. Now, solving the equation of motion for f is simply completing the square. So we'll write this as minus f by 2 and f plus I w of x squared. This generates the correct term here, but it has an extra term, which the extra term is minus, but the minus cancels because the I square. So the extra term was w squared by 2. So we need to subtract that out by hand. So w squared x by 2. Okay, so this is a parenthetic manipulation. And so all terms involving f here can just be replaced by minus wx squared by 2. Okay, and so we get x dot squared by 2 minus w x squared by 2, okay, and then whatever didn't involve f we just keep, so plus I psi chi psi dot plus w prime psi chi. Oh, and there we are. We can switch this sign because chi psi, and there we are. Okay, so better than expectation, we got it right first shot. Okay, so this action here, which we knew was supersymmetric. How did we know it was supersymmetric? We knew because we had worked out the supersymmetry from the Hamiltonian point of view. Then we converted that action into a path integral over anticommuting fields. Now we have checked directly from the path integral that the action is nice and supersymmetric. Is this clear? Okay, so that action here, that action there can be rewritten our final answer is that action is the same as minus, that's right, d theta bar minus half d theta x d theta bar x by 2 plus I of x. That is the same thing. This object is the same thing as, of course I am omitting to write integral dt. This is the same thing as integral where L is the Lagrangian mirror term. Wonderful. All good? So we've seen directly from this abstract superfield point of view that our action that we looked at was supersymmetric. This is the point of view we will usually take when we're studying high dimensional theories. It's usually not easy to find. It's just a much more convenient thing to do in more complicated theories. Okay, we will start with the path integral, or the action, the Lagrangian rather than the Hamiltonian. Now, notice one or two things. You've often heard that supersymmetry Okay, so maybe we can notice it now. So now, let us continue with our algebra for another 10 or 15 minutes. Then we get back to starting to moving. But let us, because it's the first time you're encountering all of this, we will do everything for this very simple problem where there is no physics mystery. Everything is very clear. Okay. Okay. Now you might say, well, what about the, how do the fields in our problem transform under supersymmetry? What is the supersymmetry transformation of little x, psi, and chi? Okay? And how does that compare with what we already know, or can be compared somehow? So let's see. Well, we know what operator generates supersymmetry because we studied it from the Hamiltonian point of view. So, what are the supersymmetry transformations? Are they generated by that operator? Right? Okay. So, let's see. We already know the answer to this question because the supersymmetry transformation is given by the action of q theta on the superfield. Okay? So, just like we worked out d theta on the superfield, we will now work out q theta on the superfield. Okay. So, let's work out q theta on x. Okay. So, for that, maybe we should work it out on this side so that we can see x as we do it. Let's do that here. Of q plus and q minus in the Hamiltonian format. Exactly. One of them will be q1 plus iq2, and the other one will be q1 minus iq2. Right?
But as it is written, it doesn't translate directly.
Well, as it's not even clear what it means directly. What you would have to check is that the operator, we can write down the operator. Okay, we can do, right. Let's take a minute to write down that operator. We had our q's. If somebody has their notes, they can help me with the signs. But we had our q and q bar. If I remember right, this was sigma plus or sigma minus? Sigma plus times, somebody help me or I will have to.
Q was sigma plus times P minus IW.
P minus IW x, and this was equal to sigma minus times P plus IWX. Okay. Now, we know that this sigma plus is chi. Okay? So, sigma plus is chi. So, effectively this is like q is equal to chi P minus IW of x. And q bar is equal to chi bar, psi P plus IW of x. I'm not sure whether my q and my q bar are the same or have got interchanged yet. Okay, it's one of the two. Okay. Now, we know the anti-commutation rules of operator chi and operator psi. Operator psi and operator chi anti-commute with each other. Okay? So, we can use these as operator, and P of course, P is the operator in quantum mechanics. So, we can use these canonical commutations, anti-commutations to see how each of these operators act on x, psi and chi. That will give us how these fields transform. Okay? And then you can try to match that with what we get from here. Let me leave, I should be giving you exercises. So if you don't mind, Shuman, if you note down, this can be our first problem in the first exercise, to check that these two things match with each other. Okay, great. But right now we have to have something to match with. So let's work that out. Okay, so good.
So in that case, we will have to find the commutation of q with x, etc. Right?
We would have to find, yes, the commutator or anti-commutator of q with x. Yeah, commutator of q with x, right. Right, exactly. Exactly. So in the usual way that an operator generates motion. Yeah, so that you will do in your exercise. Okay, but let's keep going with this. So we have q theta acting on x. Oh no, we were going to do it here. Please keep helping me do it as carefully as you did last time. This is great. So we've got q theta acting on x. So now let's bring x down. And here we will not, okay. Yeah. Presumably, this is obtained from d theta acting on x by switching the sign of all terms with a time derivative. Because q theta and d theta differ only in the sign of the time derivative. So let's just take it from there. Right. So that was equal to I psi minus I theta f plus I theta into x dot.
This is q bar, right?
I'm doing q bar?
That's d theta bar.
Thank you, thank you. I chi plus I theta bar into f plus x dot, because x dot switched sign, plus theta theta bar chi dot. Okay, and q theta bar x is equal to I psi minus I theta f minus x dot minus theta theta bar chi dot. Perfect. Psi dot. Thank you. Excellent. Now let us read off from this the transformation properties of x. So what is q theta on x? Let me just call that delta theta, okay, of little x. Well, capital X started with an x, but here we have an I psi, I chi. So we get I chi. That's what it means. Each component, how does it transform? Okay. What is delta theta of chi? Well, that's easy. Delta theta of chi. I hope you can distinguish my chi's and my x's is 0, because there is no theta term in q theta of x. Delta theta, maybe I should just call it delta and delta bar, but anyway, you'll excuse the notation. Delta theta of psi is equal to what? Delta theta of psi, psi was I theta bar psi, so we have an I theta bar, so this is f plus x dot. And delta theta of f, okay, delta theta of f, delta theta of f is the term which is theta theta bar, so that's minus psi dot. Sorry. Thank you. There was an I there, there's a theta theta bar here, minus I chi dot. Okay, let's also fill out the delta theta bar relations. Delta theta bar of x is equal to I psi clearly. Right? Delta theta bar of chi, this time is not 0, is equal to minus f minus x dot, so is equal to x dot minus f. Delta theta bar of psi is equal to delta theta bar of psi is 0, and delta theta bar of f is equal to, okay, this one we need our wits about us, I psi dot. Okay. Perfect. This I'm claiming is the way all the fields transform under supersymmetry. Now, before we get too happy, let us check. Okay, how do we check? Well, these transformation rules should obey the algebra. Okay, so in particular, if I act with a transformation, a delta theta twice, I should get 0. So let's see, if I act with delta theta once on x, I get chi. Second time on chi, that gives 0. Good. What about delta theta on chi? Well, that's 0. So the second one is also 0. What about delta theta on psi? This is the non-trivial one. Delta theta on psi gives us f plus x dot. Now, if I act with delta theta again on x, I get I chi dot, but f I get minus I chi dot. So they cancel. Beautiful, right? When I tried working it out just before class, it wasn't working. So you guys are. Okay. I guess some sign issue. Okay. Great. Now let's do it with the delta theta pass check. This one is trivial. The only one that's non-trivial is, oh, and what about this? That of course also works automatically because this one's 0. Right? So the only one that's non-trivial is this guy. Let's check it. We get x, and that gives us I, some beautiful, oh no. See, it's not working. Oh, it's working. Both have the same sign, and there's a minus sign here. Lovely. Wonderful, so it's working. Okay, now before we get ecstatic, okay, let's try one more check. Let's check that q bar plus q bar q gives 2I d by dt. It works? Did I hear someone say it works? So let's see. Okay, so we want delta theta bar plus delta theta bar delta theta. Let's work this out on x. Okay, so let's see. The first term was equal to delta theta of I psi plus delta theta bar of I chi. Now delta theta of I psi was equal to I into f plus x dot plus delta theta bar of I chi is equal to I into x dot minus f. So that's equal to 2I x dot. Quite remarkable. Okay, so it's 2I d by dt. Okay, I'll check the last 4 guys as well, and then we'll move away from algebra. We'll declare victory. And what about delta theta bar plus delta theta bar delta theta of chi. Well, one of them is easy, this one's 0. What about this guy? So this is equal to delta theta of x dot minus f, which is equal to I chi dot to I chi dot. Great. Delta theta on chi was 0, and therefore we acted with delta theta bar on chi. Delta theta bar on chi was x dot minus f. So now we have to act with delta theta on it. And we got this. All good? Okay. What about delta theta bar plus delta theta on psi? Well, that's sort of like the flip of this computation. We get delta theta bar on what was delta theta of psi, which was f plus x dot, and delta theta bar on f dot, that's I psi dot and x dot, x of delta theta bar, so it's equal to 2I psi dot. And last one. Delta theta plus delta theta bar plus delta theta bar delta theta on f. Okay, now that is equal to delta theta on f. So let's do the delta theta bar. So that's equal to delta theta of I psi dot plus delta theta bar on minus on chi dot. Now delta theta of right. So this is equal to I times delta theta of psi, which was f dot plus f double dot minus I times delta theta bar of chi minus I times delta theta bar x double dot minus f dot, which is equal to 2I f dot. The x double dots cancelled. Okay, so you see it works beautifully. At this stage, I could just give you these supersymmetry transformations. You can check, as we've just done, that it obeys the algebra. You can also check, as we've not done, but I'll leave it as an exercise for you. So, Shuman, next exercise, take the action, the Lagrangian expanded in without superfields, just coordinates, okay, and check that it is invariant under these supersymmetry transformations, component supersymmetry. Right? You could do that. There's no need for superspace. Superspace is just a device that allows you to easily build supersymmetric Lagrangians. Once you've got the answer, superspace is not something deep. It's not something structural or important, or at least maybe eventually in some way. Maybe we will eventually realize that there is some deep role for it. But at the moment, it's just some mathematics. Just some dumb mathematics that helps us make supersymmetric Lagrangians. Okay? Oftentimes, once you've got the Lagrangian, it's easier to think about the Lagrangian in component notation than in superfield notation. Not always, but often that's the case. Okay? It's just a device that helps you make sure that you are generating supersymmetric motion. Okay. Now, one last thing I want to discuss about. There's one last thing that I want to discuss about this this model and its supersymmetry transformations, and then we move on to other things. Okay. And that last thing goes as follows. One of your exercises was to check that the supersymmetry transformations that we've generated by this procedure, these component supersymmetry transformations, the ones we had in a box up there that I removed, is the one that you get from Hamiltonians. But some of you are thinking, what does that mean? Bosonic variable transforming into fermionic variable. Excellent. Okay, so let's go with that first. We often say that supersymmetry is transformation between bosonic and fermionic variables. In fact, that's how we started talking about supersymmetry, right? Takes bosons to fermions. Here you see, it may not have been very clear that this was what was happening in our simple toy model when we looked at it from the point of view of the Hamiltonian. Because everything was bosons. There were just two component fields. Or maybe you want to say that two component fields describe a fermion, then everything is fermions. Where are the bosons and fermions? Right, it could have been an electron we were talking about. A two component electron, okay, every state in it is fermionic. You see, the notion of fermionic here is notion of fermionic on the one-dimensional world line. Not in target space. Okay? Thought of as a quantum field theory in one dimensions. This thing has fermionic and bosonic states. And you see that very clearly in this formalism. Because we are doing a path integral over bosonic fields, commuting fields, and anti-commuting fields. The anti-commuting fields are the fermions. The commuting fields are the bosons. And supersymmetry is a transformation that takes us, a symmetry that takes a commuting field and makes it anti-commuting. An anti-commuting field and makes it commuting. That's the sense in which it interchanges bosons and fermions. Okay? When we do it in higher dimensions, like when we study four-dimensional field theories, the anti-commuting fields will be actually four-dimensional fermions. So it will become even clearer. But it always was this, except that it was Bose-Fermi symmetry on the world line. On the world line, where it's a quantum field theory in 0 plus 1 dimensions. In that sense, it was Bose-Fermi symmetry. Is this clear? Okay, thank you for that question. Okay, yeah. Now, I was going to say something else, which is the following. One of your exercises is going to be to show that these supersymmetry transformation properties are those that you get from the Hamiltonian. But now some of you are thinking, what does that mean? Because these supersymmetry transformation properties have this F. And the Hamiltonian has no F. So what does it even mean that they're the same thing? Okay? In particular, okay. Now the answer to that question goes as follows. To generate supersymmetry linearly, as we have done. So what we have done here is find a linear representation of the supersymmetry operator. Right? Because all the fields that appear in the superfield multiplet X, the transformation of them was homogeneous in fields because there was a differential operator acting on that field. So it's not like I took a linear expression, not like I took an expression of some degree, or a linear expression made it of some higher degree in the fields of the theory. Is this clear? Right? The supersymmetry transformations here, X is with chi, psi is with F plus X. There's no F square. There's no higher degree polynomial. But such transformations, linear transformations, only generate non-trivial symmetries in free theories. Whereas our theory is not a free theory. Okay? So, what this superfield formalism ensures that we have linear supersymmetry transformations. But that's not what we want. So there's a price. And the price is that the superspace formalism always appears with these auxiliary fields. The supersymmetry transformations are always linear, expressed in terms of the auxiliary fields. But the auxiliary fields, as we have seen, The auxiliary fields, as we have seen, are not true fields, but can be solved for the true fields, okay, by equations of motion. In this case, F is secretly minus IW. But you know, once we start using equations of motion in symmetry transformations, we might have to use lots of equations of motion in symmetry transformations. Okay? If you take F and plug in minus IW, once again you will find that the supersymmetry algebra closes on itself. The supersymmetry algebra works, but only once you use every equation of motion in the theory. This is exercise number 3. So, okay, most of it will be your exercise, you will work it out, but let's look at one thing immediately. What about this guy? This guy, which is that the supersymmetry transformation of F is minus I times chi dot. Okay? How could it possibly work that the supersymmetry transformation of some complicated superpotential function W is minus I times chi dot? Let's check how that works. Okay, I'll check this one thing for you, and you guys, then you guys, what you will do is ignore this, because there'll be no F left, and just substitute for F, and then check that it works. But we want to see that this also continues to make sense. So let's check that. So where should I work? Let's work here. Let's go to subspace. Okay, so we have that del theta of F is equal to minus I chi dot. But del theta of minus I W of X, okay, is equal to minus I times W prime of X times the change of X in terms of theta, okay, times I chi dot. I chi. Okay, why are these two things the same? Okay, to see that, let's go back to the Lagrangian. Is the Lagrangian, where is the Lagrangian most easily? Okay. Of course. It's, and everything is infinitesimal because we're acting with the differential operator. Del theta is a small change. In fact, for supersymmetry, there is no such thing as a large change unless you invent a new auxiliary anti-commuting parameter to multiply the supersymmetric operator with, which some people do, which I always find very irritating. I don't think you should ever think of it like that. Just supersymmetry is infinitesimal because it's acting with thetas. Okay, supersymmetry squares to 0. Okay. If you want to exponentiate, you need that. As far as I can tell, you never need to exponentiate. People, there's an industry that does this kind of thing. Okay, people develop super space by exponentiating, and well, very art. I'm not saying anything more on camera, but okay, okay, okay. But I don't think, at least for our purposes at the moment, we don't need it. It's infinitesimal, right? That's why we get this. Now, oh, I'm sorry, where the hell was our Lagrangian? Have I cleared it? There's somebody help me with it. Can somebody read out our Lagrangian to me, please? Does somebody have it written down? It was here? Oh, there it is. Ah, lovely. Sorry. So I was doing stupidity. Okay, let's look at the Lagrangian now. And now compute the equation of motion with respect to psi. The equation of motion with respect to psi tells us that I chi with respect to psi, I said, because I wanted chi's here. So first I have to integrate that by parts. So I'll get minus I chi dot minus W prime chi is equal to 0. Okay? And therefore, by equation of motion, minus I chi dot is equal to W prime chi. But here we have W prime chi because minus I and I cancel. Okay? So, once we use the equations of motion, this transformation rule and this transformation rule are the same. That's how these things usually go. When you're trying to do symmetry transformations or completely off-shell, you just get what you get. Once you start using equations of motion, you usually have to use them all.
So when we try using that operator formalism by commutation,
Yes.
the second one.
We will get the second thing. We will get either this or this. You'll actually get this, but it doesn't matter because equations of motion are true within the path integral. So there's an identity within the path integral which is expressed by the equation of motion. So these things are the same thing. Okay? So it doesn't matter. You will get these things, but you will need to use, or you may need to use, equations of motion. Okay? Notice it's working with all signs and so on. Okay, excellent. So that's the last comment I wanted to make. Everything else, by the way, so what you will want to do now is to plug, now that we've checked that these relations are consistent, what we've checked, by the way, is that this relation here is consistent with this transformation property. And we got something here and something else by varying this. Plugging that equal to that would not have been consistent. Okay? We've checked that this plugging in is consistent with these transformation properties. Now that we've done that, we can forget about this. Everywhere we have an F, we input a minus IW. And that is the correct symmetry transformation property. Symmetry transformation rule. Algebra will close using equations of motion in general. Okay? And this is what you will get, this or its equation of motion counterpart is what you will get by, from the Hamiltonian formalism. Notice that now our transformations are not linear anymore. Because W could be like some crazy function. And here you get W prime. So in the transformation of psi, which is the truly non-trivial transformation in this game, it knows about the dynamics of the problem, knows about the potential of the problem. And this thing is genuinely nonlinear. Okay? So it's a beautiful interacting theory, got an interacting symmetry transformation rule after integrating out the auxiliary fields. Okay? And everything is very nice. Okay, fine. That's all I wanted to say for this model. I was wondering, I've never worked this out. Okay, Shuman, let's be adventurous. For the problem set, let us also try to take the following. Last thing, and then this is really the end of this model. Sorry, one comment before we do that. The comment is that in this model, there is another conserved charge. And that conserved charge is spin. You see, our Hamiltonian, if you thought in terms of the Hamiltonian, had only sigma 3 in it. Okay? So if you start with spin up, you stay spin up. You start with spin down, you stay spin down. So there's a conserved charge, namely sigma 3. This, if you remember, was really fermion number. Okay, because it's the thing we use to define the Witten index. It's minus 1 to the power f. Okay? So this, by the way, of course, is the reason that when we looked at the exact solution to our problem, even though locally we found possibility of having spin up and spin down and so on, the exact wave function never did any flipping. It was some overall spin up times some function of x, or some overall spin down times some function of x. Okay? So now, of course, this is not a course for credit, so all these assignments are also up. It's up to you to do for fun, no, not to do it. That's, if you enjoy it, you do it. Okay? But so in that spirit, this is an exercise I've never worked out. But let me ask you if you can, if you want to try it. I was thinking of the following. Consider a superpotential of the following form. Okay? So for instance, we could make it concrete by giving a double hat kind of thing. Okay? Consider a superpotential of the following form. Okay? And compute the ground state energy in some approximation in the superpotential. Okay? So when we send this problem set, we'll make it more concrete. I'll give you a specific form. But the basic point is, you remember that for such models, there is no zero energy ground state wave function. But of course, there has to be a two-dimensional manifold of very low energy states. Because there was a state localized around here that was very low energy, another state localized around here that was very low energy. Okay? So, the question will be to try to compute the lifting of the breaking of supersymmetry. Okay? You could do it in many ways, but one interesting way would be to use instantons. There will be an instanton that will break this, the supersymmetry. Okay. So I've never done this myself, but it would be a fun exercise, I think. And then if you're enjoying it, you can then look at a problem with three we'll also put that in the problem set. A problem with three minima. One of those that. So here I've written, by the way, W square. So so this would be something in W, it would be of the form like this. This would be W and this would then be W square. But you could look then at a W which looks like this. Something that does have a supersymmetric. Do the same calculation. And check if you can understand why the supersymmetric vacuum is not lifted here, even though it was lifted in that problem. Just from the point of view of perturbation theory. Of this instanton kind of perturbation theory, or WKB, whatever, however you want to do it. In doing this, you will want to remember that that spin is an exact quantum number in this problem. That will help you. You never need to look at mixing between ups and downs. The only mixings that are ever relevant are between ups and ups.
What do you mean when you say supersymmetry will be broken?
By supersymmetry will be broken, I mean there is no state which is annihilated by the supersymmetry operator. Which is the same thing as saying there is no state which has exactly zero energy. Because if a state is annihilated by the supersymmetry operator, as we have seen, it always has exactly zero energy. Okay, so this ends my discussion of this model. Any questions or comments before we move on? Oh, we're almost at the end of class. Any questions or comments before we move on? Here we'll end class in 7-8 minutes. But questions or comments, otherwise we'll proceed. Okay? You may ask me, what was the purpose of spending 3 lectures on this model? It's not going to be the model that will describe physics at LHC. It will not describe black hole microstates. Why did we spend so much time on this model? Well, who knows what describes what, of course. But the real reason was that it's a very natural problem. It's a problem of an electron moving in some potential with a magnetic field. A very natural problem that has supersymmetry in it. It's kind that you could have encountered as an undergraduate without noticing it was supersymmetry. right? Your quantum mechanics course, first quantum mechanics course could easily have had this potential. Okay? It's a very natural problem, one in which every bit of intuition that you have built up through your years of study of physics is available to you. There's a Schrodinger equation, there's no infinite dimension, it's the Hilbert space is very clear, square integrable wave functions, two components. Everything is very, very much in front of your eyes. And in this model, you encounter supersymmetry, including many of its features. So the point was to introduce the ideas and the formalism of supersymmetry to you in the context of a model where the basic physics is utterly unmysterious. So anything you want to know about this model, you can compute, right? It's not rocket science. Okay? But all the formalism is there. That was the point. We will, as we move on to models where the basic physics is less clear to us and use supersymmetry to help uncover it. Okay, that's at least the goal of these lectures. Okay, fine. So, let us proceed. So, I'll take 5 minutes more and then we can really start next time. Okay, so.
Are these two Lagrangian?
Yes.
Superfield version and are these uniquely like one-to-one equivalent or?
Well, if you give me a superfield Lagrangian, I can just open it out.
Then this is the only option.
It's not, yeah. You could fool yourself in giving two supersymmetric Lagrangians if one of them differs by a term that is actually 0, right? So, like for instance, the total derivative of suppose I write something that's d theta bar. It's like you said, suppose I wrote down d theta of a superfield and integrated. It looks like it's a new supersymmetric, but it's not really. I think it's basically the same thing. Basically one-to-one.
And this is the first term of the whole series. Like it can have dx to the power 4 or something, or it can't.
What?
D theta x, d theta over x.
Ah,
Kinetic term.
that's like kinetic term. Good. Now, if you could have, now supersymmetry would not prevent you from having that. Okay? Now, those are not models we usually study because in physics we usually deal with two derivative theories. Why do we usually deal with two derivative theories? This is not very clear. But one answer is that the quantization of a two derivative theory is at least something much more familiar, at least much more straightforward than that for high derivative theories. Oftentimes you try to build high derivative theories and then you try to quantize them and you find they have unitarity problems. You see, the two derivative theory, you can move to the canonical formulation. And then from the canonical formulation you can do the Dirac business. So you build a Hilbert space. High derivative theories, those games are off. And may or may not end up making sense.
So this is the most general function you can write.
No, not most general function. Could be that, for instance, if you were integrating out some additional massive field, you would generate some high derivative terms. So it's not, I'm not claiming this is the most general thing you can write. But if you want to think of this as a well-defined autonomous theory by itself, this is a safe bet. From the point of view of supersymmetry, you might be able to do more. I mean, you will be able to do more.
So this is the two derivative general.
This is the most general two derivative action in one variable. Okay, excellent. Let us, in fact, the next thing I wanted to talk about was precisely this. So, Schumann is asking, suppose I want to stick to two derivative actions. Couldn't I have done more? Well, you might have thought, Schumann, what about adding a function of x with the kinetic term?
Yeah.
You can do that. But unless that function of x is singular, you can always do a field redefinition to make that kinetic term go away. Okay? And in fact, that's where we are heading towards. Where we are heading towards a context where that is not the case. That is when you have more than one x. Okay? So, suppose now I have a function, that's not a good point. Yeah. Suppose now I have a theory where I have some fields xi. Not just one field, but many fields. These fields are superfields. Okay? And I want to write down an action that is two derivative to start with without any potential. We will discuss potentials also in this model. It will lead to what's called Morse theory. Okay? We will discuss that. But suppose now I want to, at the moment, I want to switch off the W part. Just the kinetic term. What is the most general thing I can do? Well, if you think about it, the most general thing you can do is this. Gij of x d theta of xi d theta bar of xj Okay. Now, next time we will discuss the Lagrangian and the Hamiltonian of this theory in more detail. By the way, the first model we were doing largely for fun. This model we're doing for fun because it is fun, but we're also doing because this model and its higher supersymmetric generalizations actually often appear in the study of quantum field theory, as we will see. Small generalization that appears in the study of quantum field, sigma models. Okay. So, first question, this is the quantum mechanical sigma model, and then you can have a 1 plus 1 dimensional sigma model. Okay. But many of the general features, we're going to try to discuss the fact that this model has additional supersymmetry when the space obeys certain nice properties. That will continue to be true in high dimensional field theories as well. Okay, so sigma models in the field theory sense rather than a quantum mechanical sense. Okay, but let's first make clear, we'll stop in 3 minutes, but let's first make clear what Schumann just said. Schumann said this is a sigma model. What does that statement mean? Okay, so next time we will expand this Lagrangian in more detail. Okay, right now I just want to pick out the parts that depend on each of the xi's has a little xi plus blah blah blah. I only want to pick out the parts that depend on the little xi plus blah blah. The little xi. Okay, I want something that has theta and theta bar. So clearly from here I want to pick out the term that is multiplying by theta bar. So that term was minus I theta bar times xi dot. And from here I want the term that, and I will want plus the other way around. Bar. I want to make this Jij symmetric. Okay, but not that it will make a difference to this. So here I will get minus I theta bar xi dot, and here I will get minus I theta x j dot from this. Okay, there will be two terms, they will add up. We will look at this more carefully next time. So you see there will be a term here which when we expand out these, we will also expand out this in a theta expansion. But there will be the term which is just Gij of little x. So this will be Gij of little x, xi dot, xj dot, plus additional stuff. Now what is this Lagrangian? This Lagrangian describes the non-relativistic motion, and when we normalize it correctly, this will have a by 2, so we will take minus half of this. Okay, this will come with a by 2. Okay, and so this describes the non-relativistic motion of a particle, not in flat space, but in a space whose metric is Gij of x. is this clear? Notice that field redefinitions in this model are precisely coordinate transformations on the manifold on which the model is the particle is moving. How do you see that? Well, you see that by actually performing the field redefinition. Suppose I take x is equal to xi is equal to xi of y. Then we get xi dot is equal to del xi by del yj, yj dot. Plug that into here. So this becomes gij del xi by del yj. Oh my god. M del xj by del yn ym dot yn dot. But this is precisely the transformation rule for a metric. When you go from coordinates x to y, this is the metric in coordinates g tilde m n. So whether you used variables x or variables y, you get the same action under field redefinition. So field redefinition in quantum mechanical path integral space of fields, maps to coordinate redefinition on the manifold on which you work. So this is a geometrical quantity. You know, this action is described not by a set of coordinates, but by a manifold. There is a manifold on which you've got a particle that is moving, and it's moving in a non-relativistic way. The model, you can use you use some specific coordinates to do calculations, but the model depends not on the coordinates but on the manifold. Okay? So this is what we often refer to as a quantum mechanical sigma model, the motion of a particle on some manifold, non-relativistic motion of a particle on some manifold. Now we've built this with these d theta bars with superfield, so it's going to be a supersymmetric generalization of the motion of a model on some manifold. Now Schumann had asked me, why can't I put a function of x behind x dot squared earlier? That's just because in manifold language, in one dimensions, every manifold is flat. And you can always move to a coordinate such that the metric is 1. So there's nothing there, no fun there.
The non-trivial part is the manifold of the metric, not the metric component.
Not the coordinates. Yes. On the other hand, here in this problem, we have the ability to make curved manifolds. So we have the ability to have fun. Okay? So in the next class we will study the non-relativistic supersymmetric sigma model. And we will analyze it a little bit. Eventually we will also turn on potentials of this model. Finally then we will end our survey of quantum mechanics and then move ahead. Okay, so that's it.